Hi everyone, I'm Akhil Goyal, working as a principal engineer at Marvell, and I also work as crypto subtree maintainer in DPDK. In this session, I would like to discuss some of the new features and performance improvements that were introduced in last few releases of DPDK. So here's the agenda for today. We'll briefly discuss on the RT Crypto DPDK library and the new algorithms recently added. And after that, we have key updates on RT security library. And then we would discuss on the newly added features like MACsec, TLS, DTLS record processing, inline IP reassembly with IPsec, and RxFlow inject. RT Crypto or the Cryptodev library in DPDK is a framework to support various cryptographic operations on data. So these operations can be asymmetric operations for cipher authentication or AED. They can be algorithm chaining as well to support cipher plus authentication or authentication plus cipher kind of scenarios. They can be asymmetric operations also for algorithms like RSA, DSA, or MODX, etc. Now these operations can be based on multiple type of data. In RT Crypto library, we have support for both in-place data and out-of-place data buffers. We can also support long buffers as well as a scatter-gather list of data. For crypto operations, we can have a predefined session and multiple buffers of data can be encrypted with same session, but we can support sessionless operations also, where the session information goes with every packet, and we can perform the encryption decryption on the fly. Another type of data can be raw. In DPDK, all the buffers are referred to as mbuff, as most of the use cases are based on networking traffic only. So, but there can be cases where data can come from higher layer, which are not specifically mbuff or a network traffic. So a support of raw buffers are added recently specifically for these cases. Another set of APIs are added in crypto library to leverage the CPU specific instructions for crypto operations. For example, ARM has Neon and cryptographic extension instructions. Similarly, Intel has AVX instructions. Here are the current set of algorithms which are supported by at least one or more drivers. The ones marked in yellow are added recently, like ShangMi algorithms, SM2, SM3, SM4, and we also have support for ShangMi authentication algorithm. These algorithms are fairly tested with hundreds of test cases in the unit test application. And we also have a FIPS validation application, which PMD owners can use for the validation of their hardware using that. In the future, we are looking for adding support for asymmetric crypto algorithm like Edwards DSA. Also, since PQC, post-quantum cryptography, is picking up pace, so we can expect to have some of these algorithms to be supported in the near future, like general encryption algorithm, Crystal Kyber, and digital signatures like Dilithium, Falcon, and Sphinx. Now we move on to the RT security updates. RT security is a library in DPDK to provide protocol offload support using an inline SmartNIC or a look-aside crypto accelerator. Currently, it has support for IPsec, PDCP, DOCSIS, MACsec, and TLS record. MACsec and TLS record processing have been added recently, so we'll discuss more on these, and we'll discuss on the detail. So first is MACsec. MACsec, or the MAC layer security protocol. It is defined by IEEE 802.1e standard. It allows authorized LAN access and maintain confidentiality of data at layer 2. It may also drop packets which are modified or from unauthorized sources. Now, here we have like MACsec header details. As a plain Ethernet packet with MAC source and destination addresses with Ethertype payload. Now, if it is processed with MACsec, a new Ethertype 0x88E5 is added, and along with a sec tag. And then we have the encrypted payload followed by a 16-byte ICV. Sec tag is a 16-byte field which includes the MACsec ether type, that is 88E5, and has the fields like tag control information and association number, AN, short length, packet number for replay checks, and secure channel identifier, the SCI field. AN is a 2-bit field which is like which is used to specify what type of SA we want, what SA we want to configure. So we can have 4 SAs for particular secure channel. Next are the MACsec configurations. We have APIs to configure MACsec. For IPsec, we just had one session create API, but in case of MACsec, we need a couple of more APIs as per the protocol requirements. So the first is SA create API, which sets the keys, salt, etc. for a particular association number. So as I said, that there may be 4 SAs for one MACsec session. For the transmit side, these 4 SAs can be mapped to a single secure channel. So we have the second API to create the secure channel, that is SC. Once we have the SAs and SCs in place, we can create a RT security session with the protocol as MACsec. This will create the security entity that is called as SecY. Now for look-aside case, these configurations are enough for configuring MACsec. But in case of inline NIC, a flow is also required to be created using RT flow APIs. This is a typical MACsec datapath illustrated in IEEE standard. Here the user data is protected using the SA key of a particular AN, packet number, the secure channel identifier, and source and destination MAC addresses are also used for authentication purpose. And some of the sec tag configurations that we added in the session, we use that to create a sec tag, and we get the secure data and ICV out of it. Now at the receive side, SA key lookup happens based on association number and the SCI, which are part of the sec tag in the packet, and we validate the packet. If the packet is not valid, it will be dropped. Now the MACsec API support was added way back in DPDK 22.11, but the unit test and the PMD implementation got merged in DPDK 23.07. Currently, the only PMD which support the RT security based MACsec is Marvell CN10K ETSDev inline driver. We also have introduced an example L2 forward MACsec application for getting the MACsec performance numbers. It is currently based only on inline MACsec and is targeted for achieving line rate for any packet sizes. Now we move on to TLS DTLS record protocol. TLS is a transport layer security protocol for securing communication between the web applications on internet. It performs encryption, authentication, and integrity protection. It comprises of 2 layers: TLS handshake to establish cipher suite, and record processing for crypto processing. Currently, RT Security adds support for record processing only. here's the basic flow of TLS and DTLS record processing. When we do record write, we generate a sequence number, insert a TLS header and some padding if needed, and then generate a MAC for the complete plain text and the header. And then add the generated MAC and encrypt the plain text and the MAC generated to get the ciphertext. At the record side, we do a sequence number and a check and add the anti-replay checks for DTLS cases, and then decrypt it and verify the MAC. And then we remove the padding, etc., and header and trailer to get the plain text back. Here's the DTLS record header processing. We generate a sequence number and other information, other header information, and then along with payload, we generate a MAC. This MAC tag is added along with padding, so we create a we encrypt to get the ciphertext. In the header, we have content type to specify the type of message we are processing. It may be an alert message or a handshake message, or it can be data also. And we have a version to denote the TLS or the DTLS version. And a length field is there to denote the size of the message. In case of DTLS, we have epoch and sequence number extra compared to the TLS. TLS maintains internal sequence numbering, whereas the DTLS has explicit sequence numbering for anti-replay checks. For algorithms like MAC can be generated using HMAC, MD5, SHA-1, and SHA-256. And for encrypt, we use AES 128.256 and 3DES and RC4. Now, the TLS support in RT security APIs was added in the DPDK 23.11. We added unit test cases and driver support in DPDK 24.03 in the latest release. Driver support is available in Marvell CN10K crypto drivers. For performance, we have enhanced the DPDK test crypto perf to get the Lucaside crypto numbers. Moving on to another interesting topic, like IP reassembly with the inline IPsec. IP reassembly is a very costly operation in terms of number of core cycles required if we do it on core. And the cost increases if the fragments are also encrypted. So we can have a solution by having a hardware offload in NIC. So the NIC can attempt IP reassembly in hardware itself and decrypt the fragments also before reassembly if they are encrypted. Now we have some APIs exposed for configuring to get the capability and set some of the configurations in the PMDs, so that when a packet is coming in line, we are able to process them. For the case of IPsec packets, we can enable this by setting a configuration RT security session. There is a parameter in that is IP reassembly enable to enable the reassembly of IPsec packets. So if the driver is configured for trying out reassembly, the packets received at application layer would be segmented mbuff for each of the decrypted fragments. If the driver fails to perform reassembly, the reason may be anything like the fragments are not coming in time, so it may fail. So it will update the mbuff dynamic fields, and application can decide what to do next, whether it wants to drop those packets. So all those packets will be part of that mbuff next field. So application will need to if the dynamic field is set, application would need to traverse through the next fields to free all the mbuffs. So now I will request Anoob to
Yeah, thanks, Akhil. So I'm Anoob, Senior Principal Engineer at Marvell. I'm also the co-maintainer for RT Security Library. In this section, we would like to discuss about a new API that we added in RT Security Library, which helps in handling exception paths such as fragmented IPsec packets. First, we will do a quick recap of inline IPsec support available in DPDK via RT Security. IPsec is a network security protocol operating at IP level. It aims at protecting the complete payload. In fact, the most common use case with IPsec is tunnel mode, where we take the complete IP packet as the payload and then sense that with IP addresses that are unique to the tunnel. As shown in the slide, we can have IPsec packets get received in RT-ETHDEV, which can get internally IPsec processed, and this is what we call as inline IPsec. From applications point of view, it would be just like how checksum would be done today. With IPsec, it is quite possible that one tunnel can have multiple inner flows. So it could be like carrying traffic between multiple peers, and then one single IPsec tunnel can carry the complete traffic. So one major challenge for IPsec implementations without inline IPsec is the inability for RT-ETHDEV to distribute based on the inner IP, which is encrypted when the RT-ETHDEV first sees the packet. With inline IPsec and with required RT flow configuration, it is possible to perform ETHDEV operations such as checksum validation or RSS-based distribution after the IPsec processing is done. So this is what is shown in the diagram. So the IPsec flow that is coming from the outside, it gets internally submitted to the ETHDEV security context. After that, it can be like multiple inner flows, which again comes back to the RT-ETHDEV. So from the application's point of view, it can just do some minor verifications like whether the process is done or not, or it can just expect that the packets will be distributed based on the inner packet rather than it's based on the IPsec packet. And then it can just focus on the application processing and completely forget about the IPsec. So in a nutshell, all the heavy lifting of IPsec, be it the decryption or decapsulation, anti-replay window checks, every single thing would be done by the time application first sees the packet. So there is one important corner case that can come as depicted in the slides. So even though I described IPsec just like how we would do checksum, it's more complicated than that. And the complication is coming from the fact that it is on top of IP, which can get fragmented. In order to perform IPsec, you will need to reassemble the packet, and then only the IPsec processing can be done. So DPDK already has a notion of hardware reassembly of IP fragments in RT-ETHDEV. Just now we discussed about that. But for this discussion, let's assume that the feature is either not available or there is some limitation when compared to the software-based implementation. So typically ETHDEV features, right, as in like checksum or reassembly, it's always done as best effort. Like so RT-ETHDEV will try to do the operation, and if it's able to do that, then yeah, it sets the required flags. And if it's not able to do, by the time the application gets the packet, it will have enough information to perform the operation again. Classic case is checksum. But with IPsec, such handling is difficult. So if you look at the diagram, so there is in the ETHDEV security context, so there are these boxes IPsec SA. So IPsec SA is nothing but the context that is required for the IPsec processing. So there are few use cases where you can't even decrypt the packet unless you have access to that state variable. Okay, so yeah. So to address this problem, to handle fragmented packets which arrive at the application layer and then it would get reassembled and then to perform IPsec on it. So that's how, for that case, we added this new datapath API. It's called RT Security Inbound Packet RX Inject. So I'll first walk through how we decided to add a datapath API in RT Security library. IPsec offload with RT security was introduced as a feature that was complementing RT Ethrev and RT Cryptodev. So the library defines the control path, but doesn't define the actual data path. And so it was more like complementing the Ethrev and Cryptodev for the data path. So for Cryptodev, it would just depend on the RT Cryptodev NQ burst or DQ burst. And for Ethrev, it will just depend on the RX burst and TX burst. So the idea behind that was the barrier that is required for an existing application that is written with the plain packets in mind. It can easily get migrated to an inline IPsec capable device, and then there is no change for the application. From the application's point of view, it is just the control path. Application needs to set up the control path, configure the SAS, etc. But after that, the main data path, it will only have like very minimal checks, just like how the checksum is done. But the main problem with, all that is good. But the main problem with such an approach was, as we saw, right, there is this fragmented packet that can be like an exception case. And then because there is no dedicated data path to access the Ethrev security context, the one in the RX side, so there is no opportunity for the application to submit to the Ethrev and get it processed. Basically, IPsec processing is happening in the RT Ethrev's RX pipeline, and there is no direct access to it. So, yeah. So that's, in order to solve that, so that's how we introduce this new API, RT Security Inbound Packet RX Inject. So on capable devices from the application can reassemble a packet and push it to the Ethrev using this API, basically Ethrev security context. And so then after that, once the packet gets IPsec processed, so as you can see from the diagram, it will get pushed back to RT Ethrev. So if you are just pushing to regular RT Cryptodev, what you do is you enqueue and then the packets get received back in the application. Okay, sorry. Yeah, and it gets received back in the application. But with RX Inject, the idea is from the application we push to the Ethrev security context, and these packets will get processed just like how any other inline IPsec packets would come. So what that means is the packets will get decrypted, decapsulated, and it will be pushed back to RT Ethrev. Then any other RT Ethrev offloads that we talked earlier, right? As in, it can be checksum, or it can be inner packet parsing, it can be reassembly. All those features will be available for such packets that are re-injected. So what we have covered here is the usage of RX Inject API when implemented by security context of an Ethrev. So even though we can handle fragmented packets properly, it still cannot prevent mild reordering of fragments with respect to the regular inline IPsec packets. So what's the problem with mild reordering? First, some IPsec implementations require that there is no change in ordering. There should not be any reordering. Is a hard requirement from certain IPsec implementations. Second point is more related to how IPsec actually behaves. IPsec has a windowing mechanism where it allows only packets with a specific range of sequence numbers. So the window size is configurable. It can be like from 64 to 4096. So due to reordering happening because of the fragment reassembly and the re-injecting back, etc., with certain configurations, it is possible that the packet would be out of the window and would fail the IPsec operation. So which should be otherwise accepted. So it is quite possible that such a scenario happens. So it's not common, but it can happen in certain scenarios. To handle such cases and any other limitation with inline IPsec with Ethrev, so the same API can be used with RT Cryptodev device. In this model, the application could dedicate one worker thread or a core or whatever to receive all IPsec traffic, and then it can implement its reassembly logic. It can implement its own custom processing or whatever logic it wants to implement. And once that is done, it can again push it back to the RTE Cryptodev via RTE security inbound packet RX inject API, the same API. As shown in the figure, so after IPsec processing is done, the plain packets will again get pushed back to RTE Ethrev RX. So what this means is, for the Cryptodev submitted packets also, you get the inner checksum, you get inner packet parsing, you get reassembly, all the features that are available in RTE as RTE Ethrev offloads will be available for the inner packet. So in a nutshell, for Ethrev, the API adds fallback handling. For Cryptodev, the API provides a mechanism for inner packet parsing and distribution. Basically, leverage all Ethrev offloads for inner packet. The API tries to complete inline IPsec feature available in DPDK today. It allows application to pick its path based on what its priorities are. If an implementation is okay with mild reordering and then it doesn't have that much fragmentation, it can just stick to regular inline IPsec path with the Ethrev RX inject. But if it has like very strict requirements on ordering, or if it has some custom processing that it needs to handle, then it can just dedicate one worker thread or a core for the re-injection purpose. And then the rest of the worker threads will see it as regular inline IPsec packets coming from the wire. So with either of these options, the net throughput that the main workers would deliver would be exactly the same. There won't be any change. For the main workers, all these packets would look like regular inline IPsec packets, and that's what actually delivers the performance. So I'll quickly cover the APIs as well. So the first API is the configuration API. So we just so it's RTE security RX inject configure. So the first argument is the context. It can be Ethrev context or a Cryptodev context based on which one is required. The second one is the port ID on which you can expect the return packet, and then the enable flag. RX inject, the second one, the RTE security inbound packet RX inject. So this is the datapath API. Yeah, again, the context is the security context associated with the Ethrev or Cryptodev. Rest of the arguments are packets, sessions, and number of packets. Do note that if you are using Ethrev RX inject, so sessions need to be created with Ethrev, and when you are using Cryptodev RX inject, when you are using Cryptodev context, so then the sessions created on Cryptodev need to be used. So the API was added in DPDK 2311, and as part of the spec change, we also added the unit test. So the unit test tests both Ethrev RX inject and Cryptodev RX inject with a bunch of combinations. Today it's supported with Marvell Octeon 10 Cryptodev and Ethrev PMDs, and yeah, as far as the performance application, so we are modifying the IPsec gateway application to have one dedicated worker thread just for doing the re-injection, and then and what we are seeing is like there is no change for the rest of the worker threads. We are able to get the same performance as inline IPsec by just dedicating one core for the re-injection. Okay, yeah, that's it. Yeah, let's open for Q&A.
Any questions?
Hey, thank you, Akhil and Anoob, for sharing this session. This question is for Anoob, actually. In that second last slide, you mentioned the RX inject. Yes, this one. The RX inject enable API, right?
Yeah.
Here you mention a port ID. So is this your DPDK port or your injection port?
This is the DPDK port. So we don't have a concept of an injection port. So we are just having one inject API, and this is the port on which we are expecting the traffic back.
So how do you keep the context in that SA lookup table like, hey, SA lookup table for physical port 1, 2, there would be separate SA associated to it.
Yeah.
So are you make using of the RT mbuf metadata to tell that, oh, this packet is reconstituted from port 1, the fragments, and when I'm injecting it back, I keep that port number there?
So for the port number, we can actually, like what we do today is mbuf has a field for the port ID, right? So when we are getting a packet from the wire in the first pass itself, so the mbuf port ID would be populated.
Correct.
So then after that, when we are re-injecting, so the first argument is the context. So that is also created on that specific ETHREF.
Okay, fine. Okay. So from that, the descriptor can be picked up and the associated SA can be looked up.
Correct.
Second question is, there were two modes in IPsec inline, if I remember. One which removes a header and one which retains a header but with clear text.
Yeah, right.
Both are supported in that Octeon 10 or removal is supported?
So, so what you're talking about is the inline crypto mode versus inline protocol mode.
Correct.
Right. So for the Marvell Octeon 10 doesn't support inline crypto mode. Okay, because what we have seen is, so with inline crypto mode, what we are essentially doing is we are decrypting and leaving the
Header.
Yeah, sorry. Yeah, the header will still be intact, and application has to still decapsulate it.
Correct.
Right. And then, so the rest of the features, right? Like, I mean, I had been describing about RSS or inner packet checksum and all that. So all that will not be possible.
On Octeon?
No. On with inline crypto.
Oh, inline crypto.
Inline crypto.
But if I recollect correctly, at least with Intel's Ninantec inline implementation, after retaining it, just like the earlier DDP package that was described, the RSS, checksum, all those things were calculated for the inner payload. So that was what was using RT flow Q RSS, you were distributing it out. So just wanted to check the compatibility there. That's all.
So what we have seen is DPDK application tended to be more optimized with inline protocol. Okay. Yeah, so the applications used to be much more simpler with inline protocol, and we were able to stack up the features just by I mean, we say that at this point, IPsec is done, right? So after that, it's like plain packet, and you can perform any operations. Like it can come just like a plain packet. Okay. So the other additional difference is with inline crypto, I'm not sure if the anti-replay checks and other such features are handled. So I'm not particularly sure there. Oh, okay. But then the thing is, yeah, I mean. Okay, so that's a key differentiator. So one advantage that I remember the same problem was also addressed with inline crypto. So the way it was handled was, so when the fallback is, when there is a fragmented packet or something, the packet would directly reach to the application, and the application performs the reassembly. After that, it does everything in the software crypto.
Both options were there, but yes.
Okay, yeah, so if you're doing it in software crypto, then that means you have we'll have access to the context. Yeah. So with the Marvell Octeon 10, the context is actually cached in the hardware, and that actually helps with the anti-replay window checks, etc. Because the traffic from that security device won't choke the DRAM, right? As in for, sorry. Correct. Yeah. Right. So yeah, yeah, in a nutshell, it is possible to support inline crypto as well as inline protocol with the same API, but the utility is more for inline protocol. The challenges are also more for inline protocol. Okay. Yeah, thank you.
Yeah, one quick question. Do we have a code example of the use of RX inject?
Yeah, so we already have uniters for both Cryptodev and ETHREF, and the performance application we are just we have an internal modifications for IPsec gateway.
Don't you think it would be a good idea to show how to defragment IPsec with inject?
Okay.
I mean, like for instance, in the IPsec gateway sample code.
Yeah,
That's what
yeah.
IPsec gateway We are modifying that. We'll be submitting it soon.
Ah, okay.
Yeah. So
And for unit test cases, we already have that.
Yeah, unit test it's already merged,
Yeah.
and you are going to submit for IPsec gateway. Thank you.
yeah, so just to add on, so the way we have implemented it is we'll have a dedicated core for just doing the, not a dedicated core, just a dedicated worker thread that will just perform the RX inject. So there won't be any changes for the rest of the worker threads. So that's the way we are imagining for IPsec gateway.
Okay, thank you.
Any additional questions for Anoob and Akhil? If not, then I think we're good. Thanks, gentlemen.